All right, welcome everybody. This is Mr. Hinckley. We're going to be doing topic 10.15, representing functions as power series. This is the last lesson of Calc BC. Congratulations, everybody. You made it to the end. So we're going to be looking at a little bit more of our power series and how we can kind of manipulate them as we do functions and represent them as functions and everything. So I want to go ahead and start by just jumping right into a problem. I have this problem here. We're going to go ahead and jump into this, just kind of see what we have. All right, so we are given the following function. So we have this function here defined as a power series, and we want to find the integral, the definite integral from 0 to 1 of f of x. Well, that's kind of interesting. That's something we have not yet done, is integrating power series, but it can be done. So if I want to go ahead and find the definite integral from 0 to 1 of f of x dx, well, that's going to be the integral from 0 to 1 of this sum. Now, if you think about this sum, this is just all these terms listed out, right? Throw on a dx there. So this is just all these terms listed out. It's pretty much a polynomial, right? That's infinite. So I could go ahead and say, well, then that sum, let's go ahead and write it here. If I was to plug in 1 and do find a couple of the first couple terms of the series, that would be what, 2 x to the 1 over 4 squared. And then that would be plus, the next one would be n equals 2, would be 2x squared over, well, that'd be 4 to the third. Plus, actually, no, that would be 3 in the top, right? 3? There we go. Plus, the next one would be 4x to the third over 4 to the fourth, and so forth. So if I wanted to integrate a sum, we can do that. This is just this series here, and we would just integrate each term individually, right? But if we think about this, what is our variable of integration? Well, the variable of integration is x. So I would just be integrating every single term based on the x term. Nothing else. Everything else is just a constant, a coefficient. So if I was to do this down here, well, this, I'm integrating all these different terms. Well, then I'd be adding up the antiderivative of each of the different terms. So the integral of a sum would be the sum of the integral of every single term. So I could actually write that down here. So that would be equal to the sum as n equals 1 to infinity of every single term. So that would be the integral, we're still doing from 0 to 1, of n plus 1 times x to the n over 4n plus 1 dx. But again, what is my variable of integration? I'm integrating in terms of x. So what really matters for my integration? Well, the only thing that really matters is that term right there. All the other stuff is a constant or coefficients. So I can go ahead and even just pull that out. I can rewrite this one more time and say, hey, that's going to be the sum as n equals 1 to infinity. I can pull out all that other stuff, n plus 1 over 4n plus to the n plus 1 power times the integral of x to the n dx. And that would be from 0 to 1. So it looked daunting at first, but really all we're doing is this integral of that, really of a power here, right? Remember, the n is a constant. It's not the variable of integration. So that's just really the general form of our power rule for integration. So then that would be equal to the sum as n equals 1 to infinity of n plus 1 over 4 to the n plus 1 times, well, what's the antiderivative of that? Well, we raise the power and divide it by the new power, so that'd be x to the n plus 1 over n plus 1. And that'd be going from 0 to 1. Now, a nice little thing happened here. I have some stuff that matched, and I can maybe simplify this up. So that would be the sum as n equals 1 to infinity of, I can go ahead and say, hey, I have 1 over 4 to the n plus 1, and now I just have x to the n plus 1 going from 0 to 1. Well, can I evaluate that? Sure, why not, right? So that would be equal to the sum as n equals 1 to infinity. Really showing, I'm showing a lot of steps in this, just so you can kind of see where everything comes from. But that would be times 1 to the n plus 1 power minus 0 to the n plus 1 power, right? We evaluate it between 1 and 0. Okay. Well, that whole thing is just, well, equal to 1, right? You just have this first one over here is 0, and 1 to any power is 1, so that's just equal to 1. So that's just equal to the sum of the series as n equals 1 to infinity of 1 over 4 to the n plus 1 power. Now, that is actually an infinite geometric series that converges, so we can find the sum even of that. And so we can actually, in the end, find a value for this definite integral, which is pretty cool. So that would be equal to the sum as n equals 1 to infinity. So we can kind of rewrite this and see what's going down. I'm going to write this as 1 over 4 to the n plus 1 power. And so we can see our geometric series even better. I can go ahead and write that as 1/4 times 1/4 to the n. Well, since absolute value of 1/4 is less than 1, the series converges. Series converges. Nice convergent geometric series. Therefore, since it converges, let's go ahead and say, okay, we need our first term. That's going to be, first term, we're starting at 1, so it's not 1/4. It's going to be 1/4 times 1/4, which that would be 1/16. Our r is 1/4, so therefore our sum, which would be 1/16 over 1 minus 1/4. Well, that would be 1/16 times 4/3, because this is 3/4. And so I get an answer of 1/12. So a lot of work there, but in the end, we're able to, given this series, we're able to integrate it and find a value. So I can maybe write my answer up here. Therefore, the definite integral from 0 to 1 of f of x dx is equal to 1/12. All right? So from this, we can see, hey, I can take a series and I can integrate it. Well, if I can integrate a series, I should be able to differentiate it, and that is correct. So we have these properties here of integration and differentiation. So we have, let's say a function is defined by a power series like we see here, like we saw in the previous problem, and it has a radius of convergence, r is greater than 0. Then on the interval, so our interval of convergence, or on the interval where we have our radius of convergence centered around c, then f is differentiable and therefore continuous. Moreover, the derivative and antiderivative are as follows. And so we see, we did the integration, so we can look at that over here. We see this is exactly what we did, right? We raised our power and then divided by that new power. If I go back to the derivative, hey, it makes sense if I have x minus c to the n and I take, the derivative of that. Doesn't that make sense that I bring my power to the front and x minus c, and then I'd have n minus 1, right? Which is what Well, we have right there. Okay, so we can differentiate and integrate power series. Just remember, what is the variable of differentiation and what is the variable integration? It's going to be the x. We're not differentiating or integrating based on the n. That's the term number of the series. That is not the variable of the function. The variable of the function is going to be x. It is f of x, a function of x. All right. Another couple important things that I want to point out down here. The radius of convergence of the series obtained by differentiating or integrating the power series is the same as that of the original power series. The radius, not the interval, but the radius. So all of these, if this has radius of convergence there, that's equal to r, right? Then that's going to be the same radius of convergence for both the differentiation and integration. So we're going to see problems where we'll have, an original function will have to integrate or differentiate and determine intervals of convergence. Well, if we just find the radius of convergence for the first function, that's going to be the same for the others, and I don't have to go through, the ratio test for all three, which is nice. But it does say down here the interval of convergence, however, may differ as a result of the behavior of the endpoints. So our radius of convergence is the same, but the interval of convergence is not necessarily the same. So we'll just have to check the endpoints for each different derivative and integral that we do. All right, power series for sine and cosine. So I want to go ahead and just show, hey, we know that the derivative of sine is cosine, right? It says, we know that. If I take sine of x, and I take the derivative of it, that's going to give me cosine. It's just one of the rules that we saw. Well then, if we know, and we saw this in a previous lesson, that sine of x is equal to this power series, can I use that power series to derive the power series of cosine? Now I know I gave it to you in the list, but I did say, hey, if you forget the cosine, as long as you know sine, you can find cosine, because cosine is the derivative of the sine. So if I say sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and then we have that nth term, general term that we have over here. All right. And that is plus dot dot dot. If I want to go ahead and take the derivative of sine of x, which we know is going to be cosine of x, then I can just go ahead and take the derivative of this power series, which is just going to be the derivative of every single term. So I go down, well, what's the derivative of x? Well, that's 1. Minus, what's the derivative of this term? Remember, we're only doing it in terms of x, so that's going to be 3x squared over 3 factorial. And there's a 3 that's going to be able to cancel out right there. Bam, bam, leaves me with 2 factorial. Plus 5x to the 4th over 5 factorial. Again, 5 will cancel, leaving me with 4 factorial. Minus, that'd be 7x to the 6th over 7 factorial. Bam, bam. Leaves me with 6 factorial. Plus, dot, 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 plus. Again, we're only differentiating the term of the x term here. So this is the only one I care about. Everything else is a coefficient. So that's going to be n negative 1 to the n plus 1. I can go ahead and bring down my power. So that's going to be 2n plus 1 times x to the 2n plus 1 minus 1. So that should just be 2 to the n, or x to the 2n. Over, I'm going to expand this just slightly. That would be times that, and I see that, yep, that first part of the factorial cancels. And so there we have it. Oh, and I forgot my plus dot dot dot. So cosine of x, its power series is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. plus negative 1 to the n plus 1 times x to the 2n over 2n factorial plus dot dot dot. And there we go. So through differentiation, I was able to take my power series for sine and change it in to the power series for cosine. All right, so let's go ahead and look at problem 2 here. Problem 2, we have h of x. Let h of x be the function represented by the power series, which we have there. It says write the first 3 terms of the series for h of x. Okay, well that's pretty easy. All right, so we have h of x is going to be equal to, starting at n equals 1, so that should be x over 1 squared, plus first 3 terms, okay. All right, so that should be n equals 2, should be x squared over 2 squared, not 2 factorial, plus next we should be x cubed over 3 squared, and so forth. I'll just go ahead and write in that general. They don't ask me to, and I'm going to go ahead and do so anyways. All right, now it says write the first 3 terms and the nth term of the series for h prime. So h prime, we just go ahead and differentiate each of these. Well, the derivative of my first term would be 1 plus, that should be 2x over 4, give me 2, plus 3x squared over 9, should be 3 down there, plus dot dot dot, plus, and that would be n x to the n minus 1 over n squared. Again, things will cancel, which is nice, plus dot dot dot. So h prime of x, just to simplify and clean things up, is 1 plus x over 2 plus x squared over 3 plus dot 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 plus x to the n minus 1 over n. And that takes care of everything. I have the first 3 terms, and I have the nth term. So we are good to go. All right. So we have this one here, given that f of x is equal to sum, as n equals 0 to infinity, of negative 1 to the n, times x to the 2n plus 3 over 2n plus 1 factorial. They want us to find f triple prime of 0. So there's actually 2 ways that you could go about this. You can expand, maybe write the first 3 terms and the nth term and go down to the third derivative and then plug in 0. Or you can, just differentiate it within the sigma itself. I'm going to go ahead and do it the expanded way. I feel like that one's just a little bit more clear of what we have. So I'm going to go ahead and say, all right, well then f of x is equal to, let's go ahead and get a couple of our first terms there. So that's going to be negative 1 to the 0, well that's going to be 1. X to the 0 plus 3, so that's going to be x cubed, over, that'll be 0 plus 1 factorial, so that's just going to be x cubed. Just write x cubed. All right, n equals 1. Now that term, this is our alternator, so we're going to be now negative. Go ahead and plug in 1. 2 times 1 is 2, plus 3 would be x to the 5th, over 2 times 1 plus 1, so that'd be 2 plus 1 would be 3 factorial. All right, alternating goes now back to positive. Let's go ahead and get, let's say, n equals 2, right? So that would be 2 times 2 is 4, plus 3 would be 7, so x to the 7th, over 2 times 2 is 4, plus 1 would be 5 factorial. All right, I think that's good. Let's go ahead and write in that general term here, x to the 2n plus 3 over 2n plus 1 factorial, and we'll go ahead and say dot dot dot. Okie dokie, let's go ahead and do our first derivative. F of x equals, well, that would just be 3x squared minus 5x to the 4th over 3 factorial plus 7x to the 6th over 5 factorial plus dot 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 plus negative 1, that would be 2n plus 3 times x, and we're going to be minusing 1, so that'll be 2n plus 2 over 2n plus 1 factorial. Again, notice nothing in that general term changed except for that x part. Oh, and I forgot to say that was f prime. All right, let's go ahead and do double prime. So that would give me 6x minus, should be 20x to the third over 3 factorial plus 42x to the fifth over 5 factorial plus dot 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 plus -1. I have 2n plus 3, but now I need to drop down my 2n plus 2. And that now I minus 1 in my power again, and that would be 2n plus 1 over 2n plus 1 factorial. Dot, dot, dot. And now we're finally at our triple prime, and that gives me 6 minus, that would be 20 times 3 is 60, x squared over 3 factorial plus 42 times 5 should be 130, right? I believe 42 times 5, 10, 5 times, no, 210. Wow, I was off. So 210 x to the fourth over 5 factorial plus dot 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 plus -1. Oh, I made a mistake. Easy to fix though. Going back, I notice I forgot my n going down, so there's an n, there's an n, there's an n. All right. So I have 2n plus 3 times 2n plus 2. Now I have a 2n plus 1 times x to the 2n plus, oh, well, just 2n, right? It would be 2n plus 0 because I'm minusing 1 again, over 2n plus 1 factorial plus dot dot dot. Now I can stop taking derivatives. I can go ahead and say, well then, what is f triple prime of 0? Well, that would be 6 minus, oh, that's 0, that's 0, and that's 0. So then, that's nice. My triple prime of f at 0 is just 6. And there we go. All right. So let's go ahead and move on to this one. So problem number 4, we want to go ahead and let f of x equal to 3x minus 2x squared plus 5x cubed over 3 factorial minus 6x to the fourth over 4 factorial. We have that general term there. So it wants us to write the first 3 terms in the general term for the series for f prime of x. All right, let's go ahead and do that. So we just need to take the derivative of this infinite series. So that'll be f prime of x is equal to 3 minus 4x plus 15x x squared over 3 factorial. It only wants the first 3 terms, so I don't even have to do that next one. I'm going to go ahead and say plus, 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 dot, dot, dot. And let's get over to our next part over here. So that's going to be -1 to the n plus 1 times n plus 2. I'm going to bring down my n times times x to the n minus 1 all over n factorial. Now I can clean things up just a little bit, so I'll go ahead and do that. F prime is equal to 3 minus 4x. There's a 3 in there. 3 times 2 times 1. 3 can go into 5, so that should be 5 halves x squared plus dot 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 plus. I can also, right here, cancel out the n with the n there, leaving me with the n minus 1. So that's going to be -1 to the n plus 1 times n plus 2 times x to the n minus 1 over n minus 1 factorial plus dot dot dot. All right, so that's part A. Let's go ahead and look at part B. Let k equal to the definite integral 1 to k of f of t dt. Write the first 3 terms in the general term for k of x. Okie dokie. So k of x is equal to the definite integral I'm thinking this is a slight typo here. This should be x. Let's go ahead and change that. That will make more sense since it's a function of x. We should end up with x in the end, right? So if I want to find k of x, all I need to do is integrate every single term all the way down. So that's what I'm going to go ahead and do. And we'll just have x in there, right? So we'll have 3 x squared over 2 minus 2x cubed over 3. We want the first 3 terms. So plus 5x to the 4th over, and that would become 4 times 3 factorial would become 4 factorial. Okay. Plus dot dot dot. All right, and we are integrating this one here. So that's going to be -1 times n plus 1 times n plus 2 times x, but I'm raising my power by 1, so that'll be n plus 1 over n factorial times n plus 1. But again, that's, I can just condense down to just n plus 1 factorial. All right, and that is the integral. The first 3 terms and the general term. All right, we want to go ahead and find a power series representation for f of x equals e to the x squared. So, how can we do this? Well, first off, if we remember, e to the x is, that's just going to be 1 plus x, there it is. Remembering 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. Where our general term is going to be x to the n over n factorial, right? So if I want to find f of x, then where I have e to the x squared, then all we're doing is we are going to replace all of my x's with x squared. So that would become 1 plus x squared squared over 2 factorial plus x squared cubed over 3 factorial plus dot 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 plus x squared to the n over n factorial. Oh, and I forgot to continue my series. There we go. So then f of x would be 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus dot 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 plus x to the 2n over n factorial. And there we go. So we can substitute values and use the use that general, or not general form, it's the power series for e to the x, and that we know. We saw that we derived it earlier in our lessons, and then we just said, hey, this is one that's going to be coming up a lot. Here we go, we see that it's coming up. Okay, so you can use that and just substitute in the different things that we have. All right, so here we have let k of x equal to cosine of x squared, and we want to find out what is k times, or x times kx. X times kx, that's just pretty much just saying, hey, what's x times cosine of x squared? Well, first off, I would remind myself, hey, what is cosine of x? What's that power series that we know? Well, that one was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot 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 plus we have an alternator times, and you can do n or n plus 1 depending on where are you starting your series, right? So I'll be n times the x to the 2n over 2n factorial. So that's cosine. Well then, if I want to know what cosine of x squared is, which is my k of x, then I would have 1 minus, and I would just plug in x squared into each of those. So that becomes x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the, 12th over 6 factorial plus dot 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 plus negative 1 times the x squared raised to the 2n power would be x to the 4n power over 2n factorial. And now finally to our end result of what is x times k of x. Well, that's just x times that whole series, 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial all the way to our general nth term here. And we would just, well, distribute and multiply the x into everything. And so we'd get a final result of x minus, add 1 to each power. So that'd be x to the 5th over 2 factorial plus x to the 9th over 4 factorial minus x to the 13th over 6 factorial plus dot dot dot. And then here again we'd be just adding 1 to our power of x. And I forgot again, my alternator should have the n there. Keep on forgetting that. Just going too fast. So that'd be x to the 4n plus 1 over 2n factorial. There we go. All right, let's see. I think I just have 2 problems left I want to do, and then that'll be it. All right, it is given that we have negative 2 over 1 minus 2x equals negative 2 minus 4x minus 8x squared minus 16x cubed dot 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 minus 2 times 2x to the n minus 1 power, right? So that is the series that we're given, and we see that that's true. Makes sense because this is a geometric series, negative 2 over 1 minus 2x. So we have a first term of negative 2 and an r common ratio of 2x. And so we see, yep, that makes sense, right? Okay, so using this fact, find the function that corresponds to the following series. So what I want you to do is look at this and compare it to what we have here. What do you notice? Well, I hope you notice that this is the derivative of that. As if I have negative 2x, well, the derivative of negative 2x is negative 2. If I have negative 2x squared, well, that'd be negative 4x, and so forth. Okay? So, if I want, what they're meaning is they want you to find a function like this here, so that you can actually evaluate what we have. Okay? So I'm going to go ahead and let's call this function, let's call it g of x. Why not? So then this up here, all of this is the derivative of g of x. That is g prime. Okay? So if I want to know what g of x is as a function, well, maybe I can just take the integral of its derivative and take it backwards, right? Which we are told g prime, the derivative of this function down there, is the function -2 over 1 minus 2x. So I can then go ahead and say, all right, well, that would be the integral of just -2 over 1 minus 2x dx. So now this is just a normal integration that we're doing here. We can think about u substitution, u being 1 minus 2x, and du being -2 du. So if we do that, g of x would then be equal to, well, let's go ahead and write it the integral still. An integral would be 1 over u du. We simplify everything. And then, well, then that's equal to the natural log plus c. So g of x is equal to the natural log of 1 minus 2x plus c. Now we can go ahead and find out what that c is by thinking of, well, then what is maybe g at 0, right? What is g of 0? G of 0, if I go back into my series right here, everything, if I plug in 0, 0, 0, 0, all of those terms are 0. We don't have any constant, so g of 0 is 0. So to find out what my constant is here, I could say, hey, 0 equals the natural log of 1 minus 2 times 0 plus c. Well, this would just be the natural log of 1, which is 0, so c is equal to 0. So we can go ahead and conclude, therefore, our function of g of x is the natural log of 1 minus 2x. And there we go. All right, last problem. So on this one, we have our function as a power series here. Tell us that they want us to find the interval of convergence for f of x. And then we're going to find the derivative of f and determine its interval of convergence. And then find the integral of f and determine its interval of convergence. So let's start with A. Interval of convergence for f. Let's go ahead and do that ratio test. Limit as n goes to infinity, and we're going to go ahead and add 1 to our powers, and then times it by the reciprocal of the original. Well, I see that x to the n can go away with that x to the n there, which leaves me with the absolute value of x times the limit as n goes to infinity of just n over n plus 1. And that limit is equal to 1. So that is just absolute value of that. Now, according to the limit test, for that to converge, we need absolute value of x is less than 1. All right. So we have our interval of -1 to 1, but we need to go ahead and check those endpoints. So let's go ahead and check the endpoints. X equals 1. Let's start with -1. So that's going to be f of -1 would be this series, n equals 1 to infinity, -1 to the n over n. Well, that is our alternating harmonic series, so that converges. We've seen that before. We can use our alternating series test to show that, but that is definitely a convergent series. Whereas if I look at x equals 1, f of 1, go ahead and put that in, n equals 1 to infinity, that becomes just 1 over n. That's our harmonic series, not alternating, and that diverges. So therefore, for part A, our interval of convergence is going to be closed on -1, but open on 1. Okay, let's go ahead and look at part B. So part B, they want us to find f prime. So f prime of x, so I go ahead and I look at my series here, and we are just integrating. Variable of integration is x, so when I integrate that, that should just be n times x to the n minus 1 over n. My n's cancel, I'm left with the series n equals 1 to infinity of just x to the n minus 1. All right. So, back in slide 2, so back a ways back, there we go, we learned that the radius of convergence of the series obtained by differentiating or integrating is the same. So, do I need to do my ratio test again? I do not. All I need to do is determine the correct interval of convergence. So I need to look at my endpoints. All right. Where are we at? There we are. So let's go ahead and look at each of our endpoints. So let's go ahead and say this first. So up here, we were able to say our radius of convergence was 1, right? We're looking at centered at 0 radius, and so we had that open interval -1 to 1, so we have to check -1 and 1. Same thing here, we are centered at 0, and so our radius is still equal to 1. So all we need to do is we need to check x equals -1 and x equals +1. Let's go ahead and start with that. F prime at -1 would be the sum as n equals 1 to infinity of -1 to the n minus 1 power. Well, that is just an alternating series where we are going 1 minus 1 plus 1 minus 1 and so forth. So that diverges. All right, let's go ahead and look at x equals 1. So f prime at 1. Well, that would be 1 to the n minus 1 power. Well, that still diverges because that's 1 plus 1 plus 1 and so forth. So that also diverges. So what is my interval of convergence for this one? My interval of convergence is open, -1 to 1, open interval. So you can already see that, hey, though we had the same radius of convergence, the interval of convergence is not the same. All right, I'm going to go ahead and go back and look at, so we need to now integrate. Let's see, I'm going to go ahead, I think, and do that over here. Part C. So I want to go ahead and find the integral of f of x dx. So if I want to find the integral, remember we're integrating the x term. So if I look at my x term of x to the n, so that would be x to the n plus 1 over n times n plus 1. So that would be my integral. Now remember, we still have a radius of convergence of 1. So we just need to look at, hey, what's happening at -1 and 1? So let's go ahead and look at x equals -1. So we have our series as n equals 1 to infinity. That'd be -1 to the n plus 1 over, go ahead and write this as n squared plus n. So if I plug in -1, this is the series that I get, and I look at that series and I notice it is an alternating series. So maybe I can use my alternating series test to determine convergence or divergence on this. So if you remember, alternating series test says that the alternating series will converge if our limit as n goes to infinity of the function without the alternator, so 1 over n squared plus n, if that is equal to 0, it is, so perfect, so that's 1. And also if the function is decreasing, mainly a sub n plus 1 is less than or equal to a sub n. So if I do that, that would be 1 over, yeah, we can do that there, n plus 1 squared plus n plus 1. Is that less than or equal to a sub n? Oh, that'd be 1 over n squared plus 1. I think we can pretty much say, yeah, that's definitely going to be smaller because it's a bigger denominator than the one on the right. So that is definitely. So this converges. All right. So it converges on the left. Let's go ahead and look at the right. Positive 1. So we have the series. Oh, let's make that sigma look a little bit better. There we go. And we have negative 1 to the, oh, no, not negative 1. What am I plugging in? We're plugging in positive 1. 1 to the n plus 1 over n squared plus n, which I can go ahead and just say, hey, that looks like this, or that is this, right? Well, maybe we can use our limit comparison test. And so I'm going to go ahead and compare it to just 1 over n squared. Okay, so I'm going to go ahead and do my comparable series. And I'm going to go ahead and compare it to this 1 over n squared. And because I know that this is a convergent p series where p is equal to 2, which is greater than 1, so this converges. So I'm going to go ahead and look at the limit as n goes to infinity. I'm going to go ahead and take my first one, so that's 1 over n squared plus 1, or plus n. I'm going to multiply it by the reciprocal of that one. We're actually dividing, but there we go. And that gives me the limit as n goes to infinity of n squared over n squared plus n, which is equal to 1. Now remember, the series test, or the limit comparison says that if when I do this limit and it is finite and positive, which is, this is definitely finite and positive, then either both series either converge or both diverge. And since my p series that I had over here converges, then I'm able to say that this series converges. So I can then say, as my final concluding thought on all of this, that my interval of convergence for the integral of that original function is the closed interval from -1 to 1. So that's a very good example showing that, hey, even though we had the same radius of convergence, when we took the derivative and took the integral, we got different intervals of convergences. Same radius, but in some cases, some of the endpoints were included and some were not. All right. Well, that concludes this lesson and the final lesson of our course.